Hello, this is Tyler Stevens and Joe Fenstermacher, and this is our presentation on the conventional press and sintering of powdered metals versus the metal power injection molding. Powdered metal press process starts by adding powdered metal into a die, which is then compressed vertically with a piston. This limits the ability for a product to be designed because everything needs to fit vertically within the piston. This limits the ability to create overhangs because you need concentric pistons to be able to push different heights in the product. This also means that you can't have any internal channels because they will get compressed within the process. If you wanted internal channels, you would need to do secondary processing. The press also creates non-uniform density within the product, which can lead to problems later down the line with sintering and with mechanical properties.
So, what is metal injection molding, otherwise known as MIM? So first, you have to create a feedstock, which feedstock is just a mixture of powdered metal and wax. After you have created this feedstock, you place it in the hopper of the molder. Then this material travels through the heater, which heats up the material, making it much more of a liquid. Before this liquid is injected through the gate of the tooling part in order to fill the mold. Now, once the mold is completely filled, uh, the tooling part opens and allows the part to be released from the mold. This part is now called a green part. Now, from there, the part needs to be debinded. Uh, so you then place these green parts in acid, which dissolves all of the binder, uh, creating a very brittle and porous part. This part is called a brown part. So from there, this part then needs to go to sintering. Here, the brown part is placed in a furnace, and the part is heated up to a high temperature. At this point, the part will begin to shrink as it fills in all of the spaces where the binder used to be. Uh, this shrinkage is something that definitely needs to be accounted for during molding to create the part at a greater scale in order to account for this shrinkage. Now, one of the major benefits of this process over other processes is it can create much more complex part geometries. However, the process is limited by the size of the parts that it can create. Now, MIM has a lot more potential points of failure compared to press metals. Uh, During molding, there's a lot of pressure variance, injection speed changes, and feedstock temperature can all affect the quality of the part during molding. During debinding, you have to figure out the right acid used to dissolve the binder and how much time it takes for the majority of that binder to dissolve. During sintering, you have to determine the temperature at which you place the parts in the furnace, how long you keep them there, and account for the shrinkage that's going to occur to those parts. Uh, Additionally, even after sintering, often it requires secondary processes like resizing the parts using a press or re-reaming holes.
The initial tooling cost for injection molding is significantly higher at $30,000 to $80,000 versus for the pressing, which is only $5,000 to $30,000. The design size for injection molding is also significantly smaller at only 100 to 200 grams versus the conventional press's 2 to 3 kilograms. Injection molding also has significantly more complex designs that it's able to create versus the pressing, which has very simple to slightly sophisticated designs. Injection molding is also capable of creating 95 to 99% dense material versus the conventional pressing that can only get to 80 to 90% after sintering. This creates better material properties, especially in tension. The powder used in the conventional press is significantly cheaper at 1.5 to $15 per kilogram because it uses coarse powder versus the injection mold's finer powder, which can cost from $30 to $200 per kilogram. Conventional pressing also has a significantly higher production rate where it can produce 1,000 to 2,500 parts per hour, where injection molding can only produce 10 to 100 parts per hour. This is because injection molding has the debinding step in the process, which takes a significant amount of time and bottlenecks the production. The shrinking in the press process also is 2 to 3%, where in the injection molding, it can be 15 to 20% on the sintering step. This means that there's significantly more consideration that needs to go into injection molding for designing to accommodate for this shrinkage. Manufacturing readiness of injection molding is pretty good because the process has existed since the 1980s. So the process has been proven and the equipment is currently commercially available. However, it is still relatively expensive to purchase the powdered metal required for injection molding because there is a limited amount of suppliers. So there is a slight knock on the supply chain maturity of it. Quality control is also slightly harder than comparable processes because there's been less work done on it. So to be qualified in quality control, you need extra experience or training with the process. And lastly, there are high facility requirements because you need the injection molder, the debinder, and the sinterer, which can take up a lot of space. So you need a large facility and able to have an injection molder. Overall, our assessment is a 9 out of 10 because the process has been used and proven to work over many years, but there still is slight problems with the supply chain and the quality control, as well as needing a large area for the facility.
So what are the pressing use cases? So for one, you can create larger parts, but these parts do have to have a simpler geometry. They have lower mechanical properties. They also have a coarser surface finish. However, you can have a much higher volume of production and you have a lower operating costs. Now, the use cases for injection molding include smaller parts with a much more complex geometry, higher mechanical properties, a finer surface finish. However, you sacrifice that with lower volume productions and a higher operating cost. So for our sources, we have Advanced Powder Products. This is one of the largest part manufacturing companies in the US. They're definitely primarily focused on BIM processes, so they are likely biased towards such processes. However, they've grown a lot over the last several years and obviously made a successful company on focusing on the BIM process. Another source we use is MacMaster. It's a CNC company and just talks about the contrasting of die casting versus injection molding. Likely a fairly unbiased source since they use both processes. Another source would be Atlas Press Metals. This is a press metals company used for information on production. May be biased to say that pressed metal produces more than it actually does, but overall not a bad source.
Metal 3DP is a producer of powdered metal, and we use them for information about the differences on the powders used in pressing versus injection molding. And they're likely unbiased because they produce for both processes. Industrial Quick Search is an informational website, and we just use it for general information, so it is likely unbiased because it contains information on a bunch of different topics. MIM Parts Manufacturer is an industrial molding company, and we use it for information on the production, like units per hour. And this may be biased towards injection molding, and it might say that it produces more than it actually does.